So let me move down to chapter 5. To talk about this kind of a certain important concept. The objective in this chapter is to calculate the center of gravity. This is a physical concept. But just like what we had before, we are always trying our best to transfer any physical problem back to the mathematical problems. And the mathematical problems, they are equivalent. It's called the centroid of the area. So that's why we want to talk about the centroids in this chapter. They are always very important because in many cases the geometries are not that simple. For example, if you are trying to sieve out these the sands in different scales, the large aggregate, the medium, and the very fine, and typically you can form this kind of shape. But the question is, which point, which is acting as the center of gravity? And typically you need to use a certain concept called the centroid to identify. Okay? Physically, we call the center of gravity. In other words, the Earth exerts gravitational force at each of the particles forming a body, real body. And consider below your weight is really distributed throughout the whole body with a constant force, but small. These forces altogether can be replaced by a single equivalent force system. In other words, you need to find that point so that at this point, the resultant moment equals 0. That's the chapter 3 concept, right? So when you have a real body in any shape, each where you may have a lot of forces acting at different locations. Your job is to find a point so that when you move all the force to that point, the resultant of force, which is acting on the center of gravity, but then at that point, all the moment due to forces is equal to 0. And that's, in terms of self-weight, it is called the center of gravity. That's the location. Okay? You may say, well, for general three-dimensional problem, how can we find that point? Because typically for three-dimensional problem, you cannot find the point. Well, this is the special case of three-dimensional problem because all forces are in one direction. Due to the self-weight. It's all in the vertical direction. That's why it is still very possible. I will show you. This is a 100% physical problem. It's still a challenge for us to solve. So then we are trying to make another equivalence, or the equivalent point, which is called the centroid of the area. So the centroid of an area is analogous to the center of gravity of the physical real body. It is the center of the area. The concept of the first moment of the area is also used to locate the centroid. So in other words, this chapter we're going to talk about the first moment of area, and also we talk about the centroid. The reason we sometimes call this first moment of area because we do need to do the one-dimensional integration. And in chapter 9, which is the last chapter we need to talk about, there's another type of moment. It's called the second moment of area. And that is also called the moment of inertia. And that's very important for any structural engineering problem talking about beams or bending problems. But we're going to worry about that later. This time, we need to talk about center of area. The concept is very straightforward. Let's say we have a simple thin plate, and everywhere there is a vertical force. Everywhere. I only plot one, but it doesn't mean there's only one. Everywhere there is a parallel but vertical direction force due to the Earth's attraction from Earth, right? So all the force in this direction. Can we find a certain point? And at this point, when you move all the forces, to this point, then the resultant moment is equal to 0. If it's possible, if we're successful, then we just call this point is the centroid. Or in other words, it's called the center of gravity of a plate. Of course, you may say, how are we going to do the three-dimensional? This chapter, in fact, there are two parts, but we're not going to talk about the three-dimensional case. We talk about two-dimensional. If the geometry is very simple, for example, it's a circle, or it's a square, or it's a rectangular shape, then it's very easy. You just basically can't simply find the geometric center. But if the geometry is quite more complicated, you really have to use this, what we call the resultant moment equal to 0 concept to locate that special point. So let's say if I call this special point point G. So we're going to move all the forces. This time it's not only 3 forces, not only 10 forces, you have millions of forces. So if that's the case, in reality, when you do the summation, it should finally end up with the integration. So that's why in this chapter, we have to deal with the one-dimensional integration. How are we going to do this one? At each force, let's typically pick any one force, which is acting on this point. And that this point has two components, x component, y components. Then let's calculate the moment of this force at the arbitrary point. Let's choose point O, for example. So if we choose point O, the moment of this small force at point O should be r cross force. R is the distance vector from O to this point. In other words, it's xi plus yj. And then cross product with this w, this lowercase small amount w called the delta w. And that's the moment of this force at this point. And you add all the moment together due to other forces at different locations, then you are really writing a summation. I already split into two components, x component, y components. In fact, this is the y component, this is the x component. So then you are having this x times a little amount of this force. That is x times delta w. If it's extremely small, use a dw, and then the summation will become integration. Same thing, the y components use y. X component. This is wrong. This is let me see. This is y component. This is x component. I'm sorry. This is a mistake. This is x component. So it's y times delta w. If this delta w is very small, but everywhere you need to switch to dw and then do integration. This scenario should be equivalent to this one having a resultant force acting on this point only. You may say, how about the resultant moment? Because we picked that special point so that there's no resultant moment. So then the moment due to this force at point O, that's simply equal to, from O to this point is x bar, the distance, the x component called x bar, y component called y bar. So x bar I plus y bar j. And then cross this w. You also find out the two components. So this is the y component is x bar times w. This is the x component, it's called the y bar times w. So this one should be equal to this. This one should be equal to this. So from these two equations, we can finally identify x bar and y bar, which is the location of what we call the center of gravity. When you do the centroid area, it ends up with the same thing. Because this time, what is the dw? That's a small amount of weight, which is a specific weight multiplied with a small area. So the specific weight is called gamma, and times the volume. The thickness, let's say the thickness is t, and then the small area is called the dA. So x times gamma times t times dA altogether, that's dw. Left hand side, x bar, which is unknown, but times the total w. Total w, again, is a specific weight of this material multiplied the total area times the thickness. So you will see both left hand side, right hand sides are having gamma, which can be cancelled out, and having this thickness, which is a uniform everywhere, be a two-dimensional problem. These two will be cancelled out, so that you finally end up with x bar times a equal to integration x dA. And this one, in fact, the right hand side, x times dA, is called the first moment with respect to y-axis. So that's why originally I call this y-axis. X bar finally equal to integration x dA divided by a. So you should be able to figure out a. You should be able to figure out x dA integration. Then you can determine the centroid location in terms of x component. Y component, same thing. From this equation, w is gamma times t, a times t, same thing, but times y bar this time. And the right hand side, that's the same thing. You have a gamma times t dA. And the gamma cancelled out, t cancelled out, and this is what you have left. Y bar times a equal to y dA. Again, right hand side is called the first moment with respect to x, but then more importantly, y bar can be calculated from this integration divided by a. So these two are the important equations to identify the center of gravity, or called to identify the centroid area. So this is the fundamental two equations to determine x bar, y bar. However, most people, engineers, do not want to do integration. And then how are I going to deal with that? If that's the case, we have to memorize a few simple cases. And then we use a composite rule to identify more complicated shapes. In other words, if you deal with a more complicated shapes, you need to split this shape into a few simple shapes. And once you know the local centroid of the simple shapes, you use a composite rule to determine the overall the centroid. So we're going to talk about this concept and some special cases next time, and I'll give you some examples to let you calculate the centroid. Talking about how to calculate the centroid of an area. And the reason we are interested in calculating the centers of the centroid of area is because we want to locate the equivalent center of gravity. Okay? If we are having a simplified, very simple geometry like a circle, like a square, then we can easily identify where the self force is located. That's not a problem. The problem is if the geometries are a little bit more complicated, there's really no way you can easily pinpoint where the location is for the center of gravity. So that's why we need to talk about this chapter, which is to introduce the centroid of an area, which is analogous to the gravity, the center of gravity. So this is the physical concept, which we call the center of gravity, but this is the mathematical concept. So in a way, every time we are starting out from a physical concept, but we're always using some kind of mathematics to solve such problem. Okay? So the analogy comes like this way. So if we have all the distributed forces acting on everywhere on a two-dimensional thin plate, for example, then we should be able to find a special point so that the total amount of all distributed forces acting on this point and without having a resultant moment. And that's the concept we talk about in chapter 3. So in chapter 3, we learned that no matter how many forces, right, acting on different locations, we should be able to find a special point so that the resultant force is simply the summation of all forces adding together, and then the resultant moment happen to be 0 for two-dimensional problem. And obviously, this is a two-dimensional problem. You may say, well, if previously like this is a three-dimensional geometry, for example, right? Can we still find that point? In chapter 3, I mentioned that in general, we cannot find a point when we are moving all the forces acting on different locations for three-dimensional geometry. We cannot. However, if all the forces are two-dimensional, in other words, all the forces are parallel in a certain direction, because we're talking about the self-weight, then this is actually the two-dimensional problem. So it doesn't really matter for the geometry is two-dimensional, three-dimensional. If all the forces are always applied in certain direction, they're all parallel, then it is treated as a two-dimensional problem. In other words, we should be able to find that special point. Once we move all the forces everywhere to this special point, then we can make sure the resultant moment equal to 0. So using such concept, we are able to find out that's a special point, which is called the x bar, y bar. And mathematically, that is called the centroid of the area. So we briefly mentioned about how to determine x bar, y bar, and we finally end up with these two equations. In other words, x bar should be equal to qy over a, or x bar should be equal to integration x dA and then a. A is simply the total area of this two-dimensional rigid body. Okay, so it can be complicated, but in general, that shouldn't be not that much difficult to calculate the area. And this is the integration we have to deal with because it's no longer integration dA. You have to multiply with the x at every small, tiny area we call dA. For example, we have this dA like this. You need to multiply with x and then do the integration. So this one, in fact, is called the first moment with respect to y-axis, because if you are looking at everything in the y-axis and then you multiply with the x component of the vector, that's why it is a first moment with respect to y. Similarly, we can identify y bar, which is the y components of this centroid, equal to the integration of y dA and divided by a. So these are the two important equations allowing us to identify where the centroid is located. In other words, if we know how to calculate x bar and how to calculate y bar, then obviously we can say this point corresponding with x component, y components is called the centroid of the area, which is also the center of gravity. But on the other hand, most engineers do not want to do the real integration. You may say, wow, this is, shouldn't be that difficult. It's only one-dimensional. In general, yes. However, if this area is pretty much complicated, it's actually is a challenge for you to do the one-dimensional integration even. So then people are trying to find out if there's some other ways to, instead of doing the integration, we just simply use the summation. And the answer is yes. If we can split any complex area into a few simple one, then you really do not have to do the integration at every point. Instead, you simply write the integration as a summation. For example, this is, say, a little bit complex geometry, and our job is to find out the centroid identified by x bar, y bar. So then the first thing we need to do is to discretize this complex shape geometry into a few simple ones. So I will define what are those simple ones categorized. Okay? Simple one normally means rectangular, square, triangle, or something like a square, something like a circle or semicircle stuff. And these are something we can get a solution right away from the book. Okay, so let's say this one can be split into two triangles and one, either this is a square or the rectangle, doesn't matter. Let's say this one. These are called simple ones. So then when you do the integration, whether it's a total A, which is simply the summation of A1 plus A2 plus A3, and then the right hand side, which is the integration x dA, you simply use lowercase x bar for the local simple geometry centroid, multiply with a corresponding area, and then you add all the simple geometry's area together. And that is the equation allowing us to calculate the capital X bar, which is this. Similarly, for the capital Y bar, that's equal to the summation of lowercase y bar, that means the central for each local ones, multiply with a corresponding area for that small area, and add them together, divided by the total area, which is summation of A1, A2, A3, for example, right? So this is what we call the composite rule, allowing us to locate the overall centroid of a complex geometry, and which we are going to talk about example, just to show you how we're going to use this composite rule to get the work done. In essence, this is much more straightforward way to calculate the centroid instead of using the integration. But if you do want to use this way, then there's something we need to know. What is called simplified or simple geometry areas, and corresponding, what are those corresponding local centroid. So now I want to talk about a few simple ones. So let's say first of all, and this is the table I just copied from the book. You should have the, this chart from the book. So let's say if we have a triangular area. So if we have a triangular area, then of course we can easily figure out how to calculate the area, right? Which is half, do we have the areas here? So which is half h times the base, which is called b, right? So bh over 2, that is area calculation for any given triangular area. That's more straightforward. Then the second question is, what is the corresponding centroid just based on this simple geometry? For example, if the centroid is here at point C, then we know that this distance from the base to this point in this vertical direction, let's for the time being we call y bar lowercase, that is always equal to 1/3. So this one is always 1/3 of this total height. So that's why this y bar equal to h over 3. Just keep in mind, not all the triangular areas are located like this way. Sometimes it's tilted in the other way with 90 degrees, then that's y bar. You can still use this one. It's become x bar. So you need to be careful when you are using this one. Sometimes we use h over 3 is for x bar. Sometimes like this is for y bar. So later on when we talk about the example, we'll talk about with more details. In essence, the location of the centroid to the base, that is always 1/3 of the total height. So this is something you need to memorize, for example. Okay? So this is one of the simple geometry we can call. These other two I would like you to memorize, which are quarter circle and a semicircle. So these two are also popular ones I would like you to memorize. Or if you say, if you can understand how to derive, that's fine. Otherwise, you just have to memorize. So this is 1/3 of the total, but look at this one, which is a quarter circle. So then, what is the area of this one? The area of this one is simple, right? The whole circle is pi r squared. A quarter of it, that is pi r squared over 4. So that's the area for this quarter circle. Now, the next question is, what is the central located based on this simple geometry? Let's say this is located at point C. Then we have this so-called x bar and y bar. So x bar and y bar, in fact, are equal to each other because of symmetry. However, you need to memorize one of these. So either x bar or y bar, they are 4r over 3 pi. So that's the distance from the center of this, it's not the center, it's the circular center, to the central in terms of x-axis. And from here to here, that's also 4r over 3 pi. So these are the numbers you need to memorize as well, because sometimes we do need to deal with a quarter circle. And we should know where is the centroid located for the simple geometry. The last one is this half circle, semicircle. For the semicircle, first of all, what is the area? The area is half of the total circle. That's why it's a pi r squared over 2. This is the area of this one. And now the next question is, what is the central located? Obviously, the central located along this line, but the distance from this O to this centroid, this distance, for the time being, we call y bar, which is 4r over 3 pi. In fact, if you look at these, three are all the same. Okay, so you do need to memorize 4r over 3 pi, depending on what kind of the location we're talking about. So these are the three popular geometries I really want you to memorize. When you do homework, of course, you can look at the book at any time you like. That's not a problem. But for any test, you're not allowed to look at the book. That's why I want you to memorize these top three. Others are more complicated. So if I have these homework questions, then you can take advantage of the result from the book. But I'm not going to ask you to calculate any centroid which is based on these kind of combinations. But the top three are very popular ones. So that's why I want you to memorize. Yes?
So the first column is x bar, correct?
The first, this one is x bar. That's corresponding to the local x bars in this direction. The second column is called y bar. This is the local y bar for each scenario.
So why doesn't a triangle have an x bar?
Okay, that's a very good point. If you are saying what is the x bar, and you say, oh, how about from this point, right? So from this point to here, for example. Okay, so then in fact, that's equal to 1. In fact, it's 1/3 from here to here. So if you have this is the top vertex, for example, right? So if you have a projection of this point down to x-axis, this point, the projection of this point down to this x-axis may not be this point. It's maybe somewhere here. So from here to here, that's called x bar, should be 1/3 of, should be 2/3 of this total. But this is a little bit more complicated, in fact. So normally we don't deal with this kind of geometry. So we only deal with this geometry if you are talking about this kind of y bar, which is 1/3 of this one. Then if I say, how about if I rotate 90 degrees? If that's the case, this y bar become x bar. So we only consider just one of these two. I'm not saying we cannot calculate, but it's much more complicated. And if that's the case, you'd better use integration instead of trying to memorize something. Because first of all, you have to know what is the projection point of this vertex down to the x-axis. Okay? But that's a good question. So in other words, I cannot randomly give you any triangular and let you calculate the centroid. I cannot. I have to give you something special. And typically these these triangular shapes are either with a 90 degree, the special of the triangle with one of the angles 90 degree, or something like this, which is okay. Okay, I'll show you with one of the examples. And that is the special triangle with a 90 degree for one of the angles. Any other questions? Okay, so the bottom line is I really want you to memorize those three, okay? Now, sometimes we can take advantage of special cases. These special cases are always related with the so-called symmetry, okay? So if you see a certain geometry or area following certain geometry, a certain symmetry concept, you don't have to calculate some of the centroid location, in fact. For example, if we have this special shape with a symmetric axis along this one, because this shape and this shape are symmetric. If you just fold this 180 degree to the other end, they are identical. That's why we call this geometry is symmetric with respect to this y-axis. Okay, and if that's the case, the centroid of this geometry must be located in this y-axis. But of course, you do not know exactly where. Is it point C, or this point, or point O, or going up? You do not know. But at least you don't have to calculate both x bar, y bars. You only need to calculate y bar. In other words, x bar for this one equal to 0. Okay, so this is the symmetry you can take advantage. Just in case you have this one, immediately you know x bar equal to 0 under this two-dimensional coordinate system. Sometimes when we see this kind of structure, and then obviously you know this structure is symmetric with respect to this special B prime axis. Because it's 90 degree, there's the same length here, there's also 90 degree, same length here. Then obviously if you fold this one down here, they are identical. If that's the case, then the centroid of this complex geometry, no matter what, is going to be along this B prime axis. Although we do not know exactly where, here, or somewhere. We do not know it, but at least we know in this line. So then once you calculate one of these two, either x bar, y bar, then the other one is the same with that. You only need to calculate one. That's what I call you need to take advantage. Okay, similarly, if you have this kind of special triangle, okay, so you have this special triangle so that this triangle is symmetric with respect to this axis. Because if you fold this one with 100 degree rotation back to the other side, they are identical, then this centroid must be located in this y-axis as well. Okay, and exactly where? At this point, based on what we have just learned. So from here to here, that is 1/3 of total. Then for this one, you know that from the centroid C to B, it's called, this may not be B, this is called like a symbol D, for example, right? This D here, let's call H. So CH must be 1/3 of from here to here, the total height. Okay. Sometimes we have exactly point symmetry. So if we have this kind of geometry, and then if you say any point, you randomly pick any point, and then you rotate with 100 degrees to another one, they are symmetric. This is called a point symmetry. If that's the case, then the centroid must be in here. Okay, that's called a point symmetry. That means in every point, you can find the corresponding image point on the other side. Okay, so these are something you can take advantage if you happen to see some also symmetry features. The bottom line in general, I really want you to memorize these three. Okay, so in the second midterm and in the final, whenever you are required to calculate the centroid of an area, and most likely we're going to deal with these kind of geometries, plus something even simpler than this. I'm not listing all of them, but simpler means if you have a circle, then what is the center of the circle? That's in the center. If I gave you a square, what is the center of the square? That is the geometric center, which you can identify two diagonal lines and then the common point. That's called the geometric center, right?